Okay, guys, so hi, welcome back. Happy Monday or Tuesday. So I just wanted to do a brief video explaining the different vocabulary terms that we have for this week. So I have made some drawings for you guys to kind of help us along with this. So the first term I want to get into is valence electrons. So I know you briefly talk about valence electrons during freshman year science, journey through physical science. So basically, your valence electrons are the electrons in the atom's outermost orbitals. So they are generally in the highest principal energy level. So plain and simple, they're the electrons in the outermost orbital. Okay, so if we look here at this magnesium atom, we know that magnesium has 12 protons. We're assuming it's neutral, so we know that it has 12 electrons, and it has 3 energy levels. This electron, bear with me please, I'm not good at drawing on a computer, and this electron are in the outermost energy level, so magnesium has 2 valence electrons. Okay, moving down, the electron dot structure. Plain and simple, it's just the element symbol. So in this case, we still have magnesium with the appropriate number of valence electrons around it. So magnesium has these 2 valence electrons. So we draw 1 valence electron and then another valence electron. Okay? So it's just an element symbol surrounded by dots that represent the valence electrons of that atom. Okay, moving on. The octet rule. So this one's a little more complex. I don't know if you've ever heard of great state of 8, but this is the octet rule. So this refers to the tendency of atoms to prefer having 8 electrons in their valence shell or the outermost shell. So when atoms have fewer than 8 electrons, they're going to react to form more stable compounds with those 8 valence electrons by gaining or losing electrons. So I gave you 2 examples here. First, we have sodium. Okay, sodium has 1 valence electron in its outer shell. So gaining 7 electrons or losing 1 electron, which sounds easier? Remember, chemists are lazy, elements are lazy. They like to take the easy route. So are we going to gain 7 electrons or are we just going to lose 1 electron? We're just going to lose 1. So if sodium loses 1 electron, then your outermost shell or your valence shell is full with 8 electrons, right? So down here, sodium has lost its 1 valence electron, and we have 2, 4, 6, 8 electrons in the outermost shell for sodium. So it's happy. It's in that great state of 8. Looking at our fluorine, okay, fluorine has 9 valence electrons. No, it does not. It has 7. Miss Stone can't count. This should be 7. 7. It has 9 electrons total, but it has 7 valence electrons, okay? So, are we going to lose just 1 more? Oh my gosh, guys, I'm so sorry. I'm having a brain fart. Are we going to lose 7 electrons, or are we just going to gain 1? Well, gaining 1 is easier than letting go of 7. So if we gain 1 more electron, then our outermost shell has 8 electrons and it's happy. So see, we gained this 1 electron here, and now we're at the great state of 8. Okay, so that's the octet rule. Okay, let me figure this out. I do not want to draw her. Okay, so now there are 3 rules to follow when we're doing electron configurations, right? So first up, we have the Aufbau principle. Okay, and I know it sounds funny, but it just states that each electron occupies the lowest energy orbital first, okay? They're lazy. They're going to choose the cabin at the bottom of the hill versus the cabin at the very top of the hill. Okay? Plain and simple. Then we're going to go to Pauli exclusion principle. Okay? And again, this states that a maximum of 2 electrons can occupy a single orbital. We already know that only 2 electrons can fit in one orbital. Now we have Hund's rule. And this one I'm going to have to show you, but I promise it makes sense once you practice it a little bit. So this states that single electrons with the same spin must occupy each equal energy orbital. Each line there needs to be one arrow pointing up in each of them before you can have an arrow pointing down. Okay? So let me show you this. So Miss Stone is going to choose an element, and she's going to choose an element that does not have a lot of electrons because she doesn't want to have to draw a lot of them. So Miss Stone's going to choose sodium. Again, please forgive me for my drawing skills. That's Na. So sodium has 11 electrons. Okay? Let me get a dark blue. So for our first electron, we're going to go with the lowest energy first. So as we can see down here, this is where we have 0 energy. And if we're on a scale of 100, this is where we would have 100 energy. So as we move up this arrow, our energy is increasing. So each electron is going to occupy the lowest energy orbital first. So that is this one. So I'm going to draw an arrow pointing up to account for that spin. Okay. Are there any other lines that I can fill up for the 1s? No. So that's Hund's rule. So now we're going to go to Pauli's rule and have 2 electrons max on this one line. A line equals an orbital. Okay, so we got 2 electrons accounted for. Note that the half arrows represent an electron. So now we're going to go to 2s. Notice how 2s is slightly lower than 2p, so we got to fill the 2s before we can fill the 2p. So again, there's no equal energy, so we're just going to put our second electron pointing down. Okay, so we have 4 arrows. We have 4 blue arrows, so that means we've accounted for 4 electrons. 2p now, okay? Lowest energy first, so that's our 2p. That's the lowest energy we have available next. Okay, single electrons with the same spin must occupy each equal line or orbital before you can add the ones, okay? So this is like you with your siblings. If you have the opportunity to have your own room, you're going to have your own room. You're not going to want to double up, okay? So this sibling is going to go into this orbital, this empty room. This sibling is going to go over here, okay? So they all have the same spin. They're all pointing up, so that means they have the same spin. Now, the 3 more siblings that we have are going to have to partner up. And remember, they have a downward spin. So they're just going to go in the same line, but they're pointing down. I'm sorry, I'm out of breath. I'm not used to talking this much anymore, okay? So this is Hund's rule in action. All right, so we have 2, 4, 6, 8, 10. We have 10 electrons accounted for. Sodium has 11, so we're going to put that 11th electron here on our 3s. So this is the electron configuration and energy diagram for sodium. I know it's a little scary the first time you're seeing it. It's okay. I have a shortcut for you though. Okay? So, my clicker. We don't want to have to draw that every time we try to figure out the configuration of an atom. So, we have a shortcut, kind of. So, your electron configuration is just how your electrons are arranged in an atom. Remember, they're going to assume them being electrons are going to assume the most stable, lowest energy arrangement, and that's just what we call the ground state electron configuration, okay? So I have this notation here. Yes. So the energy level is represented by this 1, okay? The type of orbital, now remember, there's 4 different types. SPDF is represented by its letter. And then the number of electrons that are in our orbital is represented by the superscript. Okay, so, sorry, I messed this up. So let's look at a few. We have beryllium, oxygen, and then calcium. Okay, so beryllium has 4 protons, which means it has 4 electrons because we're assuming that these are neutral. So here we go. This one right here represents the energy level. So we always have to start at the first energy level. We always have to start with 1s. So let me back up a little bit. Sorry. See these purple squares? That's the S block. And then these green squares are the P block. Okay? So each box represents 1 electron. So all you have to do is look at the colors, count how many of that color you have, and that becomes your subscript, your superscript. Okay? I'll go through this with you. We're always going to start with 1s, and then the sum of these 2 teal numbers, they look black on here though, must equal the atomic number. Okay, so beryllium has 4 electrons. So we're going to start with our 1s. Okay, so we have 1, so that's where I get that 1. The purple, we're in purple, so we know that we're only in our s orbital. So we have 1, 2, so that's where we get this 2 from. Now we need to go until we get to beryllium. So now we move down to the second energy level, and we count 1, 2. Okay? So we're still in purple, so we get 2s2. I know it's confusing. I'm going to link a bunch of videos. Don't worry. Okay? So the atomic number of beryllium is 4. 2 plus 2, 4. We're good. Let's look at oxygen. Again, we need to start with 1s. So we start here, 1, 1, 2. So we get our 1s2. We go down to our 2. We got our 1, 2 purple boxes. So that's our 2s2. And then we got to go over here to our P block. Okay, it's still the second energy level, right? This is still the second energy level. And we're going to count until we get to oxygen. So we have 1 box, 2 box, 3 box, 4 box. So we're going to get 2p4. Okay, so 2 plus 2 plus 4 equals 8. Oxygen's atomic number is 8. All right, calcium, I was supposed to do this on paper, but I'm having difficulties figuring everything out. So let me just go through this, see if I can insert a text box. Yeah, I guess. So this is for calcium, okay? So, like I said, we're always going to start here. We got to get to 20. We got to get to calcium. So we're going to start with our 1 energy level, 1, 2 in the S block. So that means it's 1s, 2. Then we're going to go to 2. So we're at our second energy level now. We have 1, 2 boxes in the s block. So we know we have an s orbital that has 2 electrons in it. Now we got to go over to our 2p block. Okay, so we're in our 2p. I know it's p because these are green. So we have 1, 2, 3, 4, 5, 6. We go all the way to the end, so it's going to be 2p6. Okay? Have we made it to calcium yet? No. So now we're at our third energy level. So we're at 3s, because these are purple boxes, and we have 1, 2 of them. Not done. We got to go to aluminum. We're still in the third energy level, so it's going to be 3. The boxes are green, so it's a P. And we have 1, 2, 3, 4, 5, 6 of them. Okay? We're almost there. We're at our fourth energy level now. So we have to put a 4. We have purple boxes, so it's an X, S. And to get to calcium, we have to go 1, 2. So we need a superscript 2. Okay? So let's see. 2 plus 2 4 plus 6, 10. 2, 2 is 4 plus 6, 10. 10 plus 10, 20. So we get there. I can't type, obviously, guys. Okay, so that would be calcium's electron configuration. Let me show you the shortcut on your periodic table. This is your periodic table. Do you notice how I have highlighted 3 separate areas? Okay, everything highlighted in yellow is your S block. So theoretically, this column, and helium should be colored in yellow because they represent the S block on the periodic table. Moving over here to the pink highlights, this whole box right here represents your P block. Okay, so notice if I'm looking at gallium, I know that it's going to be 4P. Gallium's the first box, so 4P1. This gets easier if you practice. You have to practice this, okay? Ideally, I would never teach this to you remotely, but we have to. This is something we have to know if you're going on in chemistry and in science in general, okay? So the D block is here, and then the F block. Notice that these are in the same line, so you have to follow that order. So it goes 4S, 3D, 4P. See these little plus signs? They follow in there. So these guys really belong up here. So if you ever get to, say you have to do radium, I will not make you do that, maybe. It would be 7S, and then it's a little double plus, so we go 5F, 6D, 7P. Okay? I know that was a lot. I'm going to link a bunch of videos that I highly suggest you watch, because if you don't practice this, you're not going to know what you're doing. Okay? And our competency is coming up. So with that being said, I'm going to go ahead and stop this so you can get started.